everyone. Thank you for joining. My name is Nick Ristuccia. I'll be talking about what it was like to build an infrared piano. I've worked in the past as a developer advocate, curriculum developer, and game designer. If you're interested in later on, just check out what some of the code is. I have that available on GitHub. And if you'd like to connect, here's where you can find me on LinkedIn. And this will be the infrared piano. So we can see that we have a couple of IR sensors, or well, a little bit hidden. We have the LCD display, speaker, linear potentiometer. So what I'll do is I'll discuss some of the hardware. I'll talk about the software, all the layers of technology that went into making the infrared piano, and then some of the design decisions and the troubleshooting and the iteration and how that all came together to make this final product. So I'll show you a video of the piano in action, and then we'll get deeper into it.
These are sensors and devices from TinkerForge: an air quality sensor, analog joystick, linear potentiometer, speaker, LCD screen, infrared rangefinder, and there are many more. We've used some of these devices to create an infrared piano. Two IR sensors detect where you place your hand over two sets of keys. The speaker beeps at a frequency matching the note for that key. The LCD screen prints the distance detected by each IR sensor, and the linear potentiometer controls volume. The software to do this is written in C. It uses the C TinkerForge bindings, which are available from Conan Center and can easily be retrieved using the Conan C++ package manager, along with many other libraries that you may feel inspired to use as part of your own projects.
See, the initial version was programmed in C, and then I rewrote it in Rust. The reasons for that I'll get to in a minute. So let's just get back to the presentation. So why build a piano? Why not? Because I could. So I thought it would be, I want to do something cool with the sensors, and this seemed like the most doable thing to do. And I also felt like a piano would be naturally inviting. It's very easy to people to walk up and be like, "Hey, what's that? Let me play. That's pretty cool. Tell me about how you made it." And just go more. It would more naturally start a conversation about all the layers of technology, as opposed to just overwhelming people with feature after feature after feature, and risk putting people to sleep or driving them off if that seems like a sales pitch. So my background, why does it seem like this was a kind of project that I could really get into? I'd say it's because of my background in, say, robotics and games. So with robotics, the first robots that I had done were in interactive C, which is just a variant of C, but with special commands for all the effectors, like the motors and the servos, and the sensors, like the IR sensor. Sonar is fantastic. There's a camera from Carnegie Mellon University, the robotics controllers. There's Fred Martin's handyboard, which came from a lab at MIT. And there's Charmed Labs XBC, which I think Charmed Labs is still around today, but essentially it uses a Nintendo Game Boy Advanced as the processor and the interface. And then my background in games, I developed various titles for Sony, Nintendo, Microsoft. One of the projects that I worked on is pictured here, Power Gig. This is from 745 Studios. It's in the same genre as Rock Band and Guitar Hero, but it uses the guitar that actually had 6 strings. So I know I was going to talk about a piano, but as a little bonus, yeah, I'll talk a bit about the guitar. So I'm pretty sure the way this worked was that you would send a light current through each string, and then once the player pushes their finger down on a particular note on that fret, that would make contact with the little metal bars that are separating each fret, therefore completing the circuit, so you can tell exactly what notes people are playing. Pretty sure that's how it all worked. And the languages that I've used, a lot of Java, because that definitely came from my time when I was at Oracle developing Java training and certification. Also C# for the Unity game engine. Played around with C++ a bit in university, so it's been quite a while, and haven't used Rust at all until recently. Then I joined, after Oracle, went to JFrog, where I was focusing on Conan C++ manager, package manager. So a lot like if you're coming from a Java background like I am, there's Maven, there's Gradle, Conan, essentially the C++ equivalent, and then I was also working on IoT type stuff. So JFrog has a tool called Connect, which is for over-the-air updates for connected IoT type devices. And the reasons why I would do this project in C++ and Rust, when it comes to IoT, those seem to be the biggest candidates as far as the potential to offer the most performant access to hardware. All right, so getting started. We have these sensors and devices. They come from TinkerForge, which is a German company. They'll take the sensors that I want and we'll connect them via a 7-prong cable to a master brick. So the master brick can accommodate 4 of these devices, and then if you want more, you just stack the bricks on top of each other, and then you have one that's connected to a computer or even a Raspberry Pi it should work with via USB or USB-C. You have the brick daemon, so essentially it acts as a bridge with the API bindings and routes the data between the USB connections and TCP IP sockets. And then you have to install the brick viewer, very handy tool for troubleshooting. So this will give you visualize and give you reports on what the sensors are detecting, or in the case of, say, the speaker, you can tell it to produce a particular sound. Great tool. And then you just retrieve the bindings that you need. TinkerForge supports a variety of languages, so C, Go, Java, Python, Rust. But the ones I've been focusing on are C and Rust. For C, like we saw in the video, just a matter of, you create your directory and then Conan install ... which would be the previous directory where the Conan file existed. This was true as of Conan version 1. Conan version 2 recently came out, so maybe a little bit different. But for what I'm doing right here, I'm just going to specify the binaries that I require, which would be the TinkerForge bindings, and then our generators in this case are going to be CMake. And then once we have that, it's just a matter of within our source code, we're going to include the headers that we need, call functions. There's really good documentation. I found this was great for reverse engineering or just getting a sense of something basic and then building on top of that documentation from TinkerForge. And then from CMake, it's just a matter of let's go ahead and find the package. We'll link whatever libraries that we need, create our executable, run the daemon. CMake creates the files that we need for make, so run make, and then run it. Pretty similar for Rust. Create the projects, but instead of using Conan, you're going to use Conan cargo.io. So here we're going to specify again our dependency on TinkerForge. Then just call the functions, consult the documentation, build and run. As far as documentation goes, I had alluded to this earlier about why I think the documentation was so great. So if I can just show a sample of that. So here's one example. We have just a basic LCD program for Hello World. We will include our headers that we need, specify the port and the UID, and this information can be very easily obtained from the viewer. So another reason why that's a very handy tool. Oh, that is weird. Okay. So do I need to stop displaying? Okay. That'll teach me to try and do shortcuts. Okay, so we'll include the headers that we need. We'll define a couple of variables that we need, and then within the main method here, we're going to have, I know it's C, but I'm going to be using Java terminology, and perhaps that's a bit inaccurate when applied to C or C++, but for the sake of getting the message across, I'll say we have our object, which is going to be for our IP connection, and then we're going to create our reference to an LCD display, connect those together, then we'll go ahead and clear the display here, and then we just have a basic hello world. We'll push that out to the LCD display. And this was pretty cool. But when I see it printed, I thought, well, that's a little bit tiny. Can I make it bigger? Turns out, yeah, scroll down a little bit. You have options here about how you would make that just a little bit bigger. Okay, cool. So this is good for just like pushing out one single value. But it occurred to me, if I'm going to have a piano, I need to be constantly getting readings from the IR sensors. So how can I structure this code in order to be able to constantly get that? And thankfully, there is an example of that as well. In C, it'll be a callback. In Rust, it's a thread. So let's see. Okay, so here we're defining our function that is going to be used as a callback. And then a little bit later within our main method, we're going to, yes, so if you look a little bit down here, so we're saying this is a function that we want to have as our callback, and we're going to customize a little bit. In this case, we're saying every 1,000 milliseconds. That's how often we're going to run that callback and get that data. So what I did is I just shrunk it down a bit to 10 milliseconds. I thought, coming from a game design background, any amount of lag, certainly approaching 100, even 1,000 is way too much. I want to reduce the amount of lag as possible. Otherwise, the piano may be completely unplayable. But yeah, great that I have that flexibility and that I have this documentation as a resource to reverse engineer and customize and build from. So having all of that together, I found that I was able to create the basic Hello World program and just get things running really easily inside of a day, which for C++ in particular was great because there's often this nightmarish dependency management kind of thing where you have to hunt down all the everything that you need, and being platform dependent, that could be even more nightmarish. Anyways, yeah, let's get back. Okay, it is showing good. And just another some more notes about what it was like in Rust. I found that the examples weren't quite enough to get things going. I took a look at their example LCD display program and I was getting an error. I wasn't able to get it to run. So it took a bit of hunting. Thankfully, there was a forum and I found that, oh, it turns out there's a little bit of bug. So just add this one line to get things working. Really great that I was able to find that, or very relieved that I was able to find that there is a solution. Being new to Rust, I wasn't exactly sure what was going on. But yeah, you just basically have to, for every sensor device that you're going to have, I found that you needed to have something like set response, especially all to true. And coming from a Java perspective, what made this a bit challenging is that I was looking at through the lens of, say, basic object orientation, and my understanding of Rust wasn't accurate. So here's what I thought it would be, or what I thought the languages would be. So you have Java, which is supposed to be like C, C++ without the knives. What did Jim Gosling say? Knives, guns, and billy clubs of memory management. So I thought Rust was supposed to be that ease of use of Java and the object orientation of Java, but with the hardware performance of C++. Turns out that's not quite the case. Rust is a lot closer to C than it is to Java, and the advantage of Rust is that it tries to prevent some of these nightmare scenarios where maybe C gives you the freedom to set something up that once it propagates or once a program gets going becomes nightmarish to try and diagnose and fix in the wild. And what Rust does, it tries to restrict the ability to even create those scenarios from even occurring. So then it's shifting the burden to the development time. That'll come, that point will, you'll see the importance of that point in just a second. So going back to my perspective on, okay, let's treat this as like basic object orientation. What I thought I could do was create what would be the equivalent of an object in Rust as a strut. Turned out, no, I can't do that, but I really wanted to. I thought, yeah, I have this one piano, therefore it should probably be a singleton and should know about all these sensors that it'll be reading from. But no, it turns out I can't do that because these sensors don't implement the copy ability. Why do we need to be able to copy? I'll show you what I was trying to do. So I had alluded to earlier that Rust wants threads instead of callbacks. So what I thought I could do was I thought I could have one piano object with all, and it'll get the values from that one object. Each thread would be dedicated to getting a particular value. So I have this thread where I want to say, all right, linear potentiometer, keep running this, and I want to get the value. Same thing. Here's another thread. We're going to dedicate that to reading from the first IR sensor, and so on. And then later on, I can just have one other thread that's going to gather all that data and perform whatever actions are necessary. In this case, it's going to be playing a particular frequency with the speaker. But what's actually happening here is, in order to prevent the scenario of multiple threads unsafely operating on one particular object or data, what's actually happening here is Rust is actually making a copy of the my piano object. So this only exists within this scope. Similarly, my piano down here only exists within the scope here of this thread. And so even though first of all, that's actually quite. I feel like that's quite messy to have all these duplicated objects floating around. And even if I can live with that, then it's like, how do I get the data out of there? That was something that I struggled with. This seemed like a more advanced topic and something I had only learned about after the fact. But there is something called Rust channels, which is supposed to be used for getting data from one thread to another, but I hadn't wanted to explore that because it seemed like, yeah, that might be quite advanced. So what I ended up doing is just lumping it all into one thread, and I had to make a little change to the design to be able to do that. So what I normally was doing was, in the C version, I had every 250 milliseconds, I was getting data from the linear potentiometer, the volume knob, and every 10 milliseconds it was supposed to be for all the other sensors. So in order to put it all in one thread, I need all of these things to be executing at the same rate. Is there really any harm done if I change the frequency of the linear potentiometer to 10 milliseconds instead of 250? No, so I can live with that. It was, performance-wise, it seems a little bit laggy, and I suspect what's going on is that it's actually stacking all of these millisecond delays. I'd have to investigate that a little bit further, but as for right now, yeah, my favorite version would be the C version, although I'm very, very curious to give this a try in Java. And so yeah, just to summarize the difference between the two, we have, I was able to get Hello World working within one day for both. In the case of C, the piano development, the hardware-wise, that was occurring at the same time as I was programming, whereas with Rust, I had already had the thing built, and I knew all the little tricks that I wanted to have, so there's no need to focus on any design work there. It's more of the burden of how do I structure the code to be able to abide by the rules that Rust puts in place to ensure for safe development. So in summary, you'd have development time and design total of 1 to 2 weeks for C and about 1.5 weeks for Rust. So now moving on to the piano design, the iteration, the troubleshooting. How did it all come to be? How did things evolve over time? So here are some of the problems that I encountered. One of the problems is that the speaker would only make a clicking sound, or was completely silent. What I expected was, I expected a tone wherever I put my hand on the piece of paper corresponding to a note. I expected that tone to play, and I expected that to occur at a rate of every 10 milliseconds. And what I observed, no tone at all. So why would that occur? So how do I go about troubleshooting this? So the way I've been taught to troubleshoot, or the classical approach, is try only changing one variable. Then if you notice a change, then it's obvious what had been changed. And when you do that change, make it really big, so the effects are going to be, there's no mistaking that that change is consequential, and you can hone in on what exactly is going on. So I ended up increasing this delay to like 10 seconds, something really big, and then I did hear a tone. So then I kept reducing that number from 10, 5, 2, 1, and smaller. And I noticed that as I got a lot smaller, then I started hearing the clicking sound. So what this meant to me is that the speaker didn't function the way that I thought it would. I thought it'd be more of like this step function where you have silence and then boom, you're playing 440 or whatever the note may be, then back to silence again. But instead, it seems like there's this little bit of a ramp up time to be able to reach the frequency. And what I was doing when I had a very small 10 millisecond delay was that I was preventing it from reaching that full state. Just as things were kind of ramping up, I would kill it and then it would have to ramp up again. So it was always in this ramping up stage. I think that's what that clicking was. So are those my only choices? Like, do I have this lag that makes a piano unplayable, or do I have no sound and clicking? So I used a little bit of logic here to get around that. So I'll keep the same callback rate of 10 milliseconds because I want that lag to be as small as possible. And instead what I do is I play the tone indefinitely. Keep playing it as long as the player's hand is over that key, and each key is about 4 centimeters wide. And until a new value is detected outside of those bounds, keep playing that tone indefinitely, and only change when the hand goes to another key. And that worked. Okay, here's the next problem. Close distance interference. What I expected was that the expected behavior was that a piano would play a tone when an object is detected. And that worked. It's very good at detecting when something is there. If you take a look at the graph over here, here I have my hand. I think it's my hand, maybe it's like water ball or something. But yeah, here I have my hand. It's about 29 centimeters away. It's detecting that. And then I remove my hand, and it's getting a reading at like 22 centimeters away, and it's quite a bit noisy too. The spike that you see on the right side is just me putting my hand there again, and then removing it, and we're back to this noise. So I'm trying to figure out why would it do that? There's clearly nothing, well, I shouldn't say there's clearly nothing there. There is nothing 22 centimeters away, so what could be causing it to give me a reading of, hey, I think there is something 22 centimeters away? And the noise too, it's varying by about like 2 centimeters, and that seems quite a bit significant. So here's what I know, or here's the layout. These IR sensors have a distance of between 100 and 800 millimeters, and the piano keys are, the closest piano key is about 100 millimeters away. And this is also where you have this yellow rod, a little triangle right there made out of connects. One thing that I also had noticed was that if I were to hover my hand above a key instead of flat on the piece of paper, let's say I did that, say I hover my key at like my hand at like 400 millimeters, it was giving me back a reading of saying, oh, I think there's something 700, 600 millimeters away. And so I think something similar is going on right here, where this triangle, which I thought maybe this is a potential source of noise, how focused and precise can this beam be, or is it going to get interference from that triangle? I'm pretty sure that was what was going on. So what I ended up doing was I removed that yellow bar on the bottom, and then we had, I thought it was perhaps maybe a little structurally unsound or a little bit flimsy, having that yellow connector on the far right side just dangling off. So I just removed that completely, and instead I have these little legs to help stabilize it that are coming from the back instead of the front. And there doesn't seem to be any interference from those little legs as well. And so yeah, as a result of making this change, the noise I was getting, the close noise, was gone. And so yeah, from this photo you can see those little legs on the side, and you have a much bigger opening now for the IR sensors to peer through. But there's still this far distance unreliability. We've taken care of the short distance unreliability. What's happening at the long end of things? So when I have nothing there, the sensors were giving me a reading of, oh, I think something is 500 to 600 millimeters away. So why would that be the case? I think it's doing its best to try to provide a reading, but again, from my findings before, it's very good at seeing when an object is there, but it's very bad at when there is no object there, or there's something like, on the periphery kind of just slightly interfering. So I thought, okay, if it's very good at spotting where an object is there, why don't I just give it something to focus on? So that's where, well, if you can see it all the way on the right, I provided a little backstop. So it's just a big plastic case with a white piece of paper, white because I thought white would be the most reflective kind of color there, as far as like absorbing or reflecting light. And so the result here is that sometimes it would report back that it found something at 800 millimeters, but there was a significant amount of noise, so it would vary between 800 and 720. But I can live with that. The reason why is because the farthest key is 660 millimeters away. So if there's any noise beyond that, like what do I care? There's no key there, so I don't need to have any precision at the far side of things. So the solution is that gives us what we want. So fantastic. Here's another problem that I encountered. Unusable second IR sensor readings. So everything was working just fine when I just had one sensor, and that was giving me the regular keys. But then once I started connecting and programming the IR sensor that was supposed to be for the sharps and the flats, then I started getting this really weird data. So I wanted to think, okay, is this noise? No, this isn't exactly noise. Noise isn't periodic. So I'm getting this really wide variance between 55 centimeters and 30 centimeters. So I'm not exactly sure what's going on here, although I have to think there's some degree of interference between the two beams. So what exactly can I do to try and investigate that? So I tried changing the ports that the sensors were connected to. I didn't expect this to solve the issue, but I thought it might give me some insight into maybe it's prioritizing one over the other based on where the ports are plugged in. That had no effect. I thought maybe I could try raising one of the sensors off the ground, because if one is elevated like that, then maybe the beams aren't interfering with each other. That didn't quite work, and I'm actually really glad that didn't work. So the reason why, if you look at the piano right now, it's where people press their keys, it's on a flat surface, a flat table. So if you have someone that's actually quite aggressive and they want to bang the hell out of it, if they're afraid to do that, and the table can take the abuse. But if I had to do something that's designed more like an organ where I have two sets of keys, I'd need to have like books or something that I have to carry around with me in order to have that elevation. And I felt like, well, can that really take the same degree of abuse as a table? No. So a lot of negatives there. So I'm actually quite glad that solution didn't work. I thought maybe what if I tried to provide some sort of physical barrier between the two sensors to ensure that there'd be no interference. Doing that, I think, would be a significant amount of work. So I was trying to do as much tinkering as I could to try and avoid a serious redesign. So I was like dismantling and modifying stuff quite a bit. And then I found, like kind of by accident, I was turning one of the sensors in a different direction, and then the noise kind of just disappeared. I had the viewer running at the same time, so I could see what exactly was going on with that sensor. So this made me think, okay, if I just have it focus in it, if I have it point in a different direction, no interference, what if I did something like this? You take one sensor, rotate it 180 degrees so that's out of phase with the other one, and that ended up working. And that was a much easier solution than trying to build, two different levels or have this physical barrier or something like that. It took me a while to hone in on this particular solution, but I'm glad it was as easy as it turned out to be. Another problem that I encountered was laggy segment display. So I'm definitely a sucker for that like retro 80s look and feel. Although maybe this is actually, maybe this could actually be 70s or 60s. But anyways, in my kit, I had two of these segment displays. And I thought, okay, that seems quite logical. Two segment displays, two IR sensors. I'll dedicate each segment display to displaying the distance read by each IR sensor. Turns out that the updating was quite slow. And even after I turned off the program, the segment display kept on updating. So I'm thinking to myself, am I just like overloading some kind of a buffer? Like, what exactly is going on here? So I tried reducing the rate at which the callbacks occur, and I thought, okay, if I have a lower number if I wait longer in between displays, that reduce the lag. Well, it kind of did, but the number had to be quite large, at which point the inaccuracy grows at what is measuring. And so this seemed quite unusable because I wanted instant feedback. I didn't want to have to wait, or it seems like quite an unuseful tool if I'm only giving you updates every like 10 seconds as far as where your hand is. I want something that was a lot faster. And so I sadly abandoned the segment display in favor of the LCD display. It's a bit harder to read, and so that's where the big font size came in. Although when I say a bit harder to read, I liked the sharp contrast of the red of the segment display. This is, yeah, a little bit harder, but I could accept that trade-off if it means I can have the precision that I need to give the readings of what IR sensors are measuring. Okay, and yeah, there you have it. That is the end result and the piano that they had seen in the video. So yeah, thank you everyone. I'm Nick Ristuccia, I've worked as a developer advocate, curriculum developer, game designer, looking for other opportunities right now, so available for corporate gigs, weddings, and bar mitzvahs. Thank you, everyone. Are there questions? Yes.
Yeah, I think if I talk loud, okay, for the camera. Cool talk.
Thank you.
Yeah, maybe translate. We are online. Cool. Yeah, excellent. I also did quite some stuff with these IoT devices. So I was wondering, the most common choice would be Arduino, right? So what was your reason, except that it's really pluggable? That's kind of nice that these sensors just work together right from start. You have the UI, but did you also consider using Arduino, and why not?
I didn't have an Arduino, but I did have a Raspberry Pi. So one of the things that I wanted to do next was see if I can get it working from a Raspberry Pi. Also, that would have dovetailed well into JFrog connectors for over-the-air updates to connected Linux devices. So it's quite easy just to put the Linux image on a Raspberry Pi, and yeah, I was very curious to give that a try next. Any other questions?
Any chance to make it polyphonic?
Any chance to make it?
Polyphonic, so you can play multiple notes at the same time, like in a chord?
That is a great question. So I'm actually not sure if the speaker is capable of producing more than one sound. And even if it was, wherever you put your hand, the sensor would be unable to detect any notes behind it. So I think the most I could hope for at this point would be having one regular note and one sharp or flat. Otherwise, I need to have many sensors, either a touch sensor, and that's probably how a lot of electronic keyboards work too, is you have a touch sensor dedicated to each key. So sadly, I don't believe chords would be an option. That actually does remind me of one design decision that I did make that I didn't mention before. So let's say I want to go and play notes as a sharp. So then I'm going to reach my hand across the keyboard, and I'm going to get values from both IR sensors, one for the sharp and one for my arm kind of interfering with the other IR sensor. And so in that case, it's just a little bit of logic to say, well, if I get any reading at all from a sharp note, completely disregard any reading that I would get from a regular note. All right, if there's no other questions, yeah, thank you everyone for attending. Thanks.